Okay. Right, welcome everyone. Welcome to Switzerland, to Ticino, to Lugano, and here to CSCS for this PRACE workshop. I'll give you just a little background on where this PRACE workshop came into this summer school. So there's a set of seasonal schools that PRACE has been giving now for the last 2 years. And it came around to our turn to have a summer school, and we were going to do a course on multi-core and many-core programming. And then we were talking with Intel from time to time, and we thought, you know, at some point this Intel mic architecture is going to come out. Let's be a little cheeky maybe and just see if this would be a good time to actually do something on the mic. And we had a very positive response. And so before we knew it, we were changing quite a bit what we were going to do with the course, and that's why, for example, today's morning session that I'll be doing on vectorization is much shorter than I would have otherwise been going to do. But as time has gone on, as well as just being able to present the opportunity for Intel to actually give you instruction on the mic architecture, at the time we were expecting that maybe we would be able to get some Knight's Ferry and maybe a couple of demonstrations where somebody could show you what's going on. But, well, things have moved on, so that you may have found that in the last week, the Knight's Corner Xeon Phi, I think is now the official name, the new product name, is now being talked about, and some people under NDA are getting access and so on. But in particular, we actually now have two of these Xeon Phi, is that what they actually call them nowadays? So we have two Knight's Corner devices here. And so that was great. Then also the other thing we wanted as well was so that when we were talking about what we want to get out of the workshop, we said we'd like to actually find out about the mic, but we'd also like to find out from some user experiences, real people, what they've actually seen. And so we've also got people who've come across from the United States here, from NICS and from TAC, to tell us about their experiences. But there's actually even more than that. So, because you may also be aware that TAC is buying a very large system. It's going to end up being about 10 petaflops of performance, peak performance, including some Knight's Corner devices. That will be Xeon Phi then, I guess, by that stage. It'll have the stamp, yeah, exactly, Xeon Phi. So, but they currently have some test systems, and so Tommy Minyard here at the front has very graciously made it so that we can actually get access to another number of devices, the order of 6, did you say? 7. So actually there will be 9 of these Knight's Corner devices, and therefore we can actually have real hands-on experience, right? It's not just some instructions, some demonstrations. It's actually going to be the only opportunity, I understand, really, for people who have not got an NDA with Intel to get access to this, probably before Supercomputing or before the product release. So just to say who this summer school is being brought to you by, we have the obligatory PRACE receives its money under 7th Framework Program, ... thing. But the partners are actually this PRACE, there's ourselves at CSCS, there's David Henty from EPCC, Intel, of course, and TAC, the two who are really giving you the access to these machines, and NICS sending 2 people over to talk about their experiences. Right, so as I said, because of the fact that we actually want to give a lot of opportunity for the 2 days for the mic, trim down a lot of the other material that we would have given on a multi-core course. So a brief introduction to vectorization is only going to last for the morning up until about 12 o'clock, which by the time we've got coffee breaks and so on, we've only got about 2 hours. Now, some of you I know are already very familiar with the ideas of vectorization, about SIMD vectorization. Some of you have written theses, some of you have got publications, best paper awards and so on out of this sort of stuff. So some of you may just tap away and do some other work. But it's very important that for those people who aren't really aware of the power of vectorization and what it actually delivers out of modern processors, that we get this message through that without the vectorization aspect, it's no point doing much of the rest of the parallelism. You lose so much of the power. So big machines of today, if we look at a set here, I'll begin with the PRACE machines, even though they're not the largest ones, because this is a PRACE workshop. Okay, so there you've got machines that are blue gene queues. There's standard machines out of x86-based systems, such as a Cray with AMD processors, Curie machine, and the SuperMOOC machine that was just announced on the top 500 list at the last time. These are actually very powerful machines. We're talking about machines of about 3 petaflops, and Jülich will go to a blue gene queue shortly. And then we've got now a new number 1 on the top 500 list, the Lawrence Livermore Sequoia machine, blue gene queue, taking over from Riken's K machine, which was there from last time, about 10 petaflops, and then Blue Waters will be another one, and we've got Argonne's machine. Now, the thing that's common about all of these machines is that they're all using multi-core processors. There's not accelerators in most of these, although there's a little bit at Blue Waters. And so they all rely on the processor technologies that we've been moving forward with in recent years, lots of cores, but also short vector units. And if you don't use the short vector unit, then you won't get any performance. Now, to give you an example, if we were look at something like Blue Gene Q or Riken's K machine, then they're getting about 8 flops per cycle on those things. And that's because of this vector unit. If you didn't have that vector unit there, then even if you've got a multiply add, you have to divide by, say, 4. So their performance would then be nowhere near the 10 petaflops, nowhere near the 20 petaflops. It's just like throwing away a lot of the cores. So we want to actually deliver that sort of performance, then we have to actually do the vectorization. And that's because we've actually had a multi-dimensional way of growing machines in recent years, because scientists want this more computing power, more floating point power. And so we've added more processor sockets onto machines. To give you an example, the Jaguar machine at Oak Ridge was originally about 5,000 sockets, and now it's at about 40,000 sockets. Sorry, it was before it was downgraded effectively in preparation for GPUs being added. So that's one way we've been doing it. Then there's more cores. You've seen multi-core as well, but also the increasing cores getting more powerful, and this is being delivered by these short vector units. So we know that clock speed increases over. We therefore now have to add these short vector units and get good performance out of them if we want to get good performance overall in our applications. And it's sort of like an unspoken powerhouse. We all see the increasing number of cores. When you log onto a machine, you can do, on a Linux machine, cat proc CPU info and see, oh yes, I've got lots of nice new things. And there's attention therefore needed on threading techniques or other ways of getting the power out of those cores, because scalability limits on MPI for many applications do exist, whereas for threading, you can get a little bit further. But interestingly, if you look at the number of cores, the flops that we get from the vector units have actually been growing at a similar sort of rate. So over the last many years, we've gone from having 1 core to 4 cores to 8 cores, for example, but also having 1 flop per cycle, 2 flops per cycle, to 8 flops per cycle, and beyond. So if we get the best performance out of these, we have to use all those cores and all get the best out of the vector units. If you don't vectorize your code, if your code isn't being vectorized, so therefore you're in the scalar unit, it's just like throwing away spare cores in some way. And you wouldn't go onto a multi-core processor and say, I'm quite happy to just use one of these things. You'd find some way of using it. So we should be really doing the same with the vectorization. So what are these vector units? So these are a method of achieving parallelism out of one instruction. So it's a parallel machine. Cores are generally parallel. They will issue several instructions at the same time, a load, a floating point operation, an integer operation. But here we can actually get data parallelism from one instruction. And this is important because actually doing the decode of the instruction in the processor is actually quite a costly thing. If you can amortize that cost by using it on a lot of data, then that's very good. They're typically described in terms of the width in bits, because this means it's easy to describe then whether it's a single precision or a double precision. You can just do a little bit of maths. So a 64-bit unit, well, 64-bit describes a double precision number, or two single precision numbers. So we'd refer to as 64-bit, 128-bit, and 256 bits, and so on. 128-bit is your SSE instructions, your typical SSE instructions these days on something like an Intel Westmere processor. 256-bit is AVX instructions on a Sandy Bridge. And then we'll move forward 512 bits onto the mic. So what happens is multiple data items are loaded all at once into a vector register, and then the instructions work on those registers. Now, on some processor architectures, the processor can issue more than one floating point vector instruction per cycle, such as the Intel Westmere, and if you're not using the vector units, you actually lose out even more than just the width of the vector unit. And this is simply the way that parallel execution would work, and I'm typically a Fortran programmer, but I believe this to be the silk syntax for how you would do some sort of operation vector-wise. But it's very close to Fortran, so I'm happier with that. And effectively, you come along, you have a scalar instruction, A, B, C, D. It's just working on one element at a time. In this particular case, you could say, I want to work on all these blocks at a time. That would actually just be, each case there would just be loaded into one register, one instruction given out, one decode. It's nice and lightweight. So how much can we gain through these vector units? Well, the performance improvements that we're looking at that we require is to be working on regular data. That is data that's laid out in a fashion where we can say to the data, all of this data needs actually to have the same instruction issued against it. Okay, so this is typical in most applications that we work with in high-performance computing. If you don't have that sort of regularity, you can't use any other type of device either. A GPU requires regularity. There may be some differences in the way that you lay out the data and the way it can access the data slightly, but we just have to have the same instruction being issued against lots of pieces of data. We also have to have instructions that can do that at the same time. But the performance gains then depend on the architecture of the particular machine you're on. Now, here we're going to be looking at, in the practicals this morning, using a cluster we have which has Intel Westmere processors. The practicals are very simple, but should expose to you some of the issues that we're looking at with vectorization and the performance gains you can get. I'll just introduce at this time a distinction, because you should hear this over the next couple of days, between big core and little core. Okay, so this is particularly what Intel have been describing, big core being something like a Sandy Bridge processor, and little core, the cores that are on the mic, to distinguish the two. So how do we get access to these vector units? So there are a number of different ways. You could program directly in assembly language, but most people aren't going to do that. But maybe some library developers would. Some people will use intrinsics. Certainly there's one person in the middle of the room I know definitely will be playing around with intrinsics on this, which is like doing it with assembly language, but you remove some of the complexity of having to worry about necessarily what register name and so on you're getting. You just know you're going to get the instructions you require. We can use an auto-vectorizing compiler, and that's what we're really going to look at today. You could also use language structures or languages themselves that can expose those short vector units. So, for example, a type like a float4 or something similar that maybe people have used in GPUs as well, that you might be able to use from a language such as OpenCL. But one other message is that if you see somebody else has already written a library, an auto-vectorized library, sorry, not an auto-vector, a vectorized library, then you should look at using that. For example, nobody really should be ever writing their own matmul unless it's a highly specialized, really small or something special. Most of the time you go along and you grab a vendor-provided BLAS or similar. So as I said, we're going to be looking at the compilers and what they can do and what they can tell us, the auto-vectorizing compilers. And so they're just able to take loops in serial code and identify whether or not this is a good target for vectorization. It's not just as simple as just looking at one loop. Normally there'd be a lot of loop transformations, triply nested and higher nested loops. The compiler will use all sorts of techniques to actually be able to say, this is something that I can identify as vectorizable. Sometimes it might identify something as vectorizable and not vectorize it because it says it wouldn't be profitable. But it has a lot of scope, and it means that we can get parallelism even though we've written a code that's a serial code. Effectively, it's going through the set of instructions, and the way we wrote it was to go one at a time, and the compiler can find a way of saying, well, actually, I think you can do more than one at a time. And then you have to have the appropriate instruction set for the architecture, so typically people would look at SSC and AVX, but you may get access to a Blue Gene Q and have the quad Hummer, for example. And so we're going to demonstrate the power of auto-vectorizing compilers about now. Okay, so the first of these examples is really quite simple. It's just a simple vector addition. Okay, so we're just going to see what speed up we get from a very simple vector addition. So I'd like you to try with GCC and ICC, or G-Fort and I-Fort. The different commands are with GCC there. We're having the OpenMP, by the way, just because I want the timer from OpenMP. There's no OpenMP in these things. With O2, which doesn't vectorize by default, and then with the F-tree vectorize, which does. On the other hand, with ICC, it's the other way around. It does vectorize by default, and we have to switch it off. Okay? So if you can just go through the simple DP and simple SP examples, see what the timings are. We're also going to look at the actual value that gets put out at the end. Is it different between vectorized and non-vectorized codes? And then play around with the vec size and iterations, and just why did we actually pick vec size being 1,000 in this case?